Welcome back to Neural Intel. One of the things that really blows my mind is how AI is learning to see depth from just a single image, kind of like we do.
It is pretty amazing.
It's called monocular depth estimation.
Or MDE for short.
MGE, exactly. And this research paper we're diving into today called Distill Any Depth.
Huh.
Well, they've come up with some really clever techniques to make those MDE models even better.
Yeah, it's a really fascinating area of research, especially because we're essentially trying to give AI this 3D understanding of the world from a simple 2D image, which, as you know, doesn't inherently have any depth information.
Right, it's like trying to figure out how far away something is just by looking at a photograph.
Exactly.
So how do researchers even begin to train AI to do something like that?
Well, one common approach is to use what are called pseudo-labels. And essentially what that means is you're using depth maps that were generated by other models, potentially more complex models, to kind of guide your new MDE model.
Okay, so it's like using a pre-existing map to help the AI learn a new route. But I'm guessing it's not quite that simple, is it?
You're right, there's a catch. These pseudo-labels, even the ones from the best models out there, well, they have some noise or errors in them. And what this paper really uncovered is that a common practice called global depth normalization actually makes that noise problem even worse.
Wait, so something researchers were doing to try and improve the data was actually introducing more errors. How does that even happen?
Well, global depth normalization, it tries to make the depth map consistent in terms of scale and shift across the whole entire image. Think of it like adjusting the brightness of a photo based on the average brightness level.
Okay, I'm following you.
The problem is if there's an error in one part of the image, this normalizing globally can spread that error to the entire depth map and really mess up the details.
Ah, I see. So it's like trying to fix the color of one spot in a photo and accidentally changing the colors of everything else in the process.
Exactly, and the researchers actually visualize this in the paper. They have a figure 2, I believe it is, and it shows very clearly how aligning depth maps globally can end up making specific regions less accurate.
Okay, so global normalization is out. What's the solution then? How do we get the benefits of these pseudo-labels without all that noise?
That's where this paper's big innovation comes in. It's called cross-context distillation, and instead of looking at the entire image at once, they focus on smaller local regions during training.
So it's like the AI is learning to see depth in fine detail, like zooming in on those intricate parts of the image.
Precisely.
But doesn't that risk missing the forest for the trees? How do we get that big picture back?
That's a great point, and the researchers address this with something they call local global distillation.
Local global distillation.
Imagine this. You have your student model that's trying to generate a full global dex map of a scene. At the same time, you have your teacher model that's creating these super detailed depth maps, but only for small sections of that same scene.
So the teacher model is like a master artist providing close-ups while the student is trying to paint the entire landscape.
A perfect analogy, and by comparing the student's overall depth map to the teacher's detailed close-ups, in those areas where they overlap, you can create this loss function that encourages the student to learn both the fine-grained details and the overall depth consistency.
Wow, that's really clever.
Yeah, and figure 3 in the paper illustrates this beautifully if you want to check it out.
I'll definitely have to take a look. It makes me wonder, though, does our own brain process depth information in a similar way, maybe with this mix of local and global cues?
It's a really interesting parallel, isn't it? Now, here's where it gets even more interesting. The researchers take this distillation concept a step further, and they actually use multiple teacher models, each with different strengths.
Multiple teachers. It sounds like AI is getting a serious education here. But what's the advantage of having more than one teacher?
Well, think of it this way. Some models might be incredible at picking up those tiny details, but they might take a really long time to process, while other models might be faster and more accurate overall, but not as good with the fine details. So by combining the knowledge of different teacher models, you're essentially giving that student model a more well-rounded learning experience.
So it's like having a team of expert instructors, each specializing in a different aspect of depth perception.
Exactly.
What kind of teacher models did the researchers use for this?
They used two very interesting ones. GenPercept, which is diffusion-based and known for its ability to capture those fine details, and Dep Anything V2, which is based on Dino V2, and it really shines in terms of overall accuracy.
And of course, there's a figure for this too.
There is Figure 6, provides a nice visual overview of this whole multi-teacher framework.
This all sounds incredibly promising, but I'm really curious, did all this fancy distillation actually work? Did it lead to better depth estimation?
Well, you're going to love this. The results are pretty amazing. This new method With its cross-context and multi-teacher distillation, it actually outperformed a bunch of the previous top-performing models.
Oh, wow. So it actually worked.
It did, and especially on these data sets known for being really tough, like DIOD and ETH3D. These are the ones with all sorts of challenging scenes,
Hmm.
indoor places with weird lighting, outdoor shots with things moving around, even different weather conditions.
So it's not just good in the lab. It can
Mhm.
actually handle the messiness of the real world. That's what we really want to see.
Exactly. And when you look at the numbers in tables 4 and 5, the improvements are really clear.
Okay, so what are we talking about here? Give me the highlights.
Well, they measured the accuracy using a couple different metrics, like absolute relative error, ABSREL for short,
Okay.
and 10-1 accuracy.
I'm a big picture person. Sometimes the numbers get a little lost on me. Break those down for me. What do those metrics actually tell us?
Sure, so basically, ABSREL tells you, on average, how far off the model's depth predictions are. From the real depth, the lower the ABSREL, the more accurate the model is.
Okay, makes sense.
Gemmer 1 accuracy is another way to measure how many of the model's predictions are within a certain margin of error. So higher Gemmer 1 accuracy, the better.
Got it. So lower is better for abs roll, higher is better for epistride accuracy. Simple enough.
Right, but they didn't just show numbers.
Yeah.
There's a way to actually see this improvement side-by-side images.
Oh, perfect. I love that.
Figures 7 and 11 are where it's at. You can actually see the quality difference in the depth maps. They're sharper, more accurate, and it's especially noticeable in those tricky real-world scenes. And when it comes to those little details, like the edges of objects.
So this isn't just like a small improvement. This is a visible leap forward.
Right.
And you mentioned earlier that this method works even when the teacher and student models are totally different.
Yeah, cross-architecture distillation.
Cross-architecture distillation, right?
Yeah.
That was the term. It's kind of like if you learned a skill from someone who speaks a completely different language,
Yeah.
the way they explain it might be different, but you can still get the knowledge.
Exactly. And in this case, it means you can use this method even if the teacher model is built very differently from the student model.
So this isn't just like a one-off trick. This is like a fundamental learning strategy that could be applied really broadly.
It is, and they even tested this with two really different model architectures, Midas and Depth Anything, and still got much better results than the standard approach.
Hmm.
Table 3 in the paper has all the details on that if you want to dig in.
We started with this basic idea, AI learning depth, from a single image. And now we're talking about noise, local versus global, multiple teachers. It's amazing how much complexity goes into making these systems work.
It is, and it's a great example of how AI research builds on itself. You start with a basic concept, you encounter challenges, and then you come up with these increasingly clever solutions.
Okay, before we go any further, I have to ask, what does all this mean for the real world?
Yeah.
What can we actually do with these better MDE models?
Well, think back to those applications we mentioned at the beginning, robotics, self-driving cars, augmented reality.
Right.
Imagine robots that can navigate cluttered environments with more ease, like delivering packages in a busy city street or assisting with rescue missions in a disaster zone.
So we're talking about robots that can do things that are really dangerous or difficult for humans. That's incredible.
Exactly. And what about those self-driving cars? More accurate, depth perception means safer, more efficient autonomous driving systems.
Right.
Imagine cars that can more accurately judge the distance to pedestrians, other vehicles, obstacles, even in really challenging conditions.
And AR too, right? Augmented reality. Could this lead to AR experiences that are more realistic, more immersive, blending seamlessly with the real world?
Absolutely. And think about creating incredibly detailed 3D models from just a bunch of photos.
Mhm.
We could virtually reconstruct historical sites or even entire cities with amazing accuracy.
The possibilities are pretty much endless. It really feels like we're on the verge of some major breakthroughs in all sorts of fields, thanks to these advancements in MDE.
I'm personally feeling super inspired by all this. It's amazing how these abstract ideas are actually translating into real-world tech with so much potential.
I completely agree, and who knows what's next? Maybe one day we'll have MDE models that are so good they can actually outperform human vision in certain tasks.
Okay, now that is a mind-blowing thought. We'll definitely have to save that for another deep dive.
Yeah?
But for our listeners who want to explore the nitty-gritty details of this research, we've got a link to the full paper on our website. It's in the bio.
And while you're there, check out our other deep dives into the latest and greatest in AI and machine learning. We're constantly exploring new research and breaking down the complex stuff into bite-sized pieces.
It's wild to think that just a few years ago, this whole idea of a computer understanding depth from a single image, it was practically science fiction. And now we're talking about models that could be even better than human vision in some ways. It really shows you just how fast this fuel is moving. And this paper is a perfect example of how researchers are constantly pushing the boundaries. They're not just, making small tweaks here and there. They're coming up with entirely new approaches to training these models.
What I find so exciting is that this isn't just theoretical research.
Yeah.
This has very real and direct implications for so many different areas, from how robots interact with the world to the future of self-driving cars and even how we experience augmented reality.
Absolutely. And as these AI systems, as they become more and more sophisticated, it's even more important for us to really understand how they work, what they're good at, and, maybe where their limitations might be. That's why these kinds of deep dives are so crucial.
I totally agree. By breaking down these research papers, we can all get a much better grasp of the complexities of AI
Hmm.
and its potential impact on, our lives, and hopefully spark some curiosity and inspiration in our listeners along the way.
I like to think that somewhere out there, someone listening to this might be the next researcher to make a groundbreaking discovery in MDE. Maybe they'll build on the ideas in this paper or come up with something entirely new.
That's a great point. The future of AI is literally being shaped right now, and who knows what amazing applications we'll see in the years to come.
Yeah, it's a really fascinating time to be following this field.
Couldn't agree more. And on that note, a huge thank you to you for joining us on this incredible deep dive into the world of monocular depth estimation.
It was my pleasure. Always happy to geek out about the latest AI research.
And to all our listeners, if you want to delve even deeper into the technical details, don't forget to check out the link to the full research paper on our website. You can find it in the bio along with a whole bunch of other fascinating deep dives on all the latest and greatest in AI and ML. Until next time, keep those neural networks firing.